What is going on, guys? Welcome back. In this video today, we're going to go through a full data science / machine learning process to predict flight prices. So we're going to train regression models to predict flight prices based on information like the airline, the departure time, the arrival time, flight duration, and more. So let us get right into it. Alright, so we're going to use regression to predict flight prices in this video today. And this is going to be, as I mentioned, a full machine learning process. So we're going to do exploration, pre-processing, train test splitting, training, evaluating, and even hyperparameter tuning. So this is a perfect video for those of you guys who want to actually practice machine learning concepts using a hands-on example. And what we're going to do in this video is we're going to work with the flight price prediction dataset from Kaggle. You will find a link to it in the description down below. All you have to do is you have to log into Kaggle, download the dataset, and the file that's important to us is going to be the clean dataset CSV file. So we can double click it, and you can already see we have some columns that definitely need to be pre-processed because most features, as you can see, are not numerical. We have stuff like the airline and source city and stops and so on. And then we also have the target variable, the price, which is what we're trying to predict with our regression models. So this is what we're going to be working with. Now, what's special about this video today is that we're going to be integrating a tool called Pieces into our workflow and into our process. And Pieces is essentially an AI workflow copilot. They're sponsoring this video today. You can go to their website. You will find a link in the description down below. In a nutshell, as I said, they're an AI workflow copilot with horizontal integration, which means it integrates into multiple different tools at multiple stages in your workflow. You can have it as a browser extension. You can have it as a JupyterLab extension. You can have it in PyCharm and VS Code. You can have it as a desktop application. And I'm going to showcase a couple of features of Pieces as we go through this video, as we go through the process of this machine learning project with a focus on the JupyterLab extension. But let me just briefly show you what Pieces can do so that you have an idea of what this tool is. It's completely free. You can download it and you can work also with Pieces as we go through this tutorial, even though, of course, it's not mandatory. You can also follow along normally. Basically, on Linux, what you can do is you can just use snap to install it. So on Debian-based distributions, it's sudo snap install Pieces OS. Then also Pieces for developers. So Pieces OS is basically the runtime. Pieces for developers is the desktop application. Then you can run both. And then you can also install the browser extension, JupyterLab extension, whatever. In the case of the JupyterLab extension, you just have to go pip or pip3 install Jupyter_Pieces. And once you have that, you just have to run Pieces OS on your system, the runtime, and then everything can connect. So Pieces OS is running, as you can see. And let me just show you one simple use case, and then we're going to explore more features as we go on. Let's say I want to go to Stack Overflow and see how to flatten a list. So Stack Overflow, flatten list of lists. This is something I want to do. Now, what I can do is here on the website, I can enable my Pieces add-on in the browser. And you can see that underneath every code sample, I have this copy and save button, which basically takes this and turns it into a piece in my Pieces application. So I have this flattened list code. I can just copy and save. And since this is integrated into my Jupyter Notebook environment as well, I can just go to the Pieces add-on here and I can click on this snippet that I just copy pasted now. And then basically I can just copy and paste it here. That's one simple use case. What I can also do is I can use the desktop application Pieces for developers to see all my pieces that I have gathered over time. I can ask the Copilot to tell me something about it. So I can start a conversation with an LLM and I can say, what does this code do? I mean, actually, it already tells me what the code does, but I can say, where would I use this if I have some questions? And the good thing about this is that Pieces is local first. It respects your privacy, it's secure, and all the user data is stored on your device. You can even use on-device LLMs, but you can also connect it to stuff like GPT. So this is like the basic idea of Pieces. You have this AI assistant, you have these code snippets, and you can manage them across multiple environments. And as I said, they're sponsoring this video, which is why they're included here. And we're going to explore some features. We're going to use Pieces a little bit as we go through this process here. So let us get started with the actual project. So as we saw, we have this CSV file and we have these different columns that definitely need to be pre-processed. So we're going to start by importing pandas as PD. Now, maybe we should first install the packages that we need for this video today. And these packages are going to be, of course, pandas, NumPy, matplotlib, and sklearn or scikit-learn. I think that should be all. Otherwise, we're going to install additional packages as we go. But the important thing, first of all, is to load the data set into pandas. So we're going to say df equals pd read CSV, and we're going to read the clean dataset CSV file. So this is going to just load our data frame or load our CSV file into a data frame. Then we can just look at it and we see that we definitely have a column that we don't need, the unnamed column. We have an airline that we probably want to use, but it's a categorical feature, obviously, and we cannot use it just as simple strings. We have the flight, which should be irrelevant. Now, maybe certain aspects of that flight, like maybe the leading characters, could be interesting, but overall, I think about dropping this feature. Source city is probably going to be relevant. Destination city is going to be relevant. Departure time and arrival time are definitely going to be relevant. You can also see these are categorical. They're not specific times, so it's not a numerical feature. It's not an ordinal encoding that we need here. It's a one-hot encoding because we have these categorical features. Then for stops, we have 0, 1, and probably also other values. We're going to have to explore this. But this definitely needs to be encoded numerically because this is a feature that can be on a numerical scale. And then we have the class, which is probably, I assume this is going to be the most important feature. And then also the flight duration. And the days left could also be interesting because it basically says, okay, how many days ahead of time are you booking a flight? And then we have our target variable, which is price. Now, what we want to do here is we want to get an idea of how many different values per feature we have. So let's say, for example, the airline. What kind of airline values do I have? How many are they? Do I want to encode all of them? So let's go and say df airline, and we're going to use the value counts function to actually get an idea of the different airlines. And you can see we only have 6 different airlines, and because of that, it makes sense to encode all of them as a binary feature. So to say, is it this airline, yes or no? Is it this airline, yes or no? Which means we're going to one-hot encode the features. Now let's do the same thing for source city and destination city. So we're going to go and say df source city value counts. And you can see we don't have too many values here. We can go destination city value counts, and also not too many cities here. So as long as we don't have too many values here, we can just use one-hot encoding. If you have a feature with 1,000 different values, one-hot encoding might not make a lot of sense, especially not on all of them. Maybe then you want to pick the top 5 values or something. But since we have a very limited amount of cities and a very limited amount or number of airlines, we can just one-hot encode all of them, or the whole feature. So then we're going to also look at arrival time and departure time. These should also not be super crazy. So departure time, value counts. There you go. And then also the same thing with the arrival time. Yeah, so we don't have too many values here either. What would be interesting now is to know how many stops, how many different stops values we have. So df stops value counts. Because if it's just 1 and 0, we could binary encode it. But since it's 1, 0, 2 or more, we can do an ordinal encoding, meaning it's 1, 0, or actually 0, 1, and then 2. All right, and then we're going to also look at class. We're going to look at duration. Even though duration, probably we can leave it as it is. Maybe we can scale it, but we don't need to actually pre-process it, like really pre-process it in terms of encoding it somehow, because it's already numerical. But let's go with the class. I think we're not going to be able to do it like this because class is a Python keyword. So let's go class value counts. And we only have 2 values, which means that this is going to be a feature that we binary encode. So we're going to make this a 0-1 feature, not a, I mean, it's the same thing as making it a numerical feature in this case, but it's not the same as encoding it, one-hot encoding it, because one-hot encoding it would mean we have an economy feature and a business feature, and they can each be 0 and 1. And in this case, we're just going to say class is 0 or 1. All right, so for the duration, maybe it makes more sense to not look at specific values, but at min and max or something like this. So yeah, we have value counts is probably not too interesting. Yeah, so let's go with min. Okay, this is the shortest flight. Then we have the longest flight, and then we can go for something like a median value to know, to get a feeling of what a normal value is here. 11. I think this is hours, right? I think so. And for days left, it's also a numerical feature, so I don't think we need to encode it. So what we're going to do in a nutshell here is we're going to drop this one. We're going to one-hot encode this one. We're going to drop this one, and basically one-hot encode these and these. We're going to turn this into a numerical feature from 0 to 2. We're going to turn this into a binary feature, and we're going to leave these 3 as they are. That's the plan for the pre-processing here. And I hope you understand the reasoning behind this, because we have these kinds of values here. We don't have too many categories if we do a one-hot encoding, and I explained why we do a numerical here and a binary encoding here. All right, so we're going to start by just doing what I just said. So we're going to, maybe let me use a markdown heading here. So we have a section pre-processing, because this above is just the exploration. And now we're going into the pre-processing. So we can say df, actually let's drop the features first. So we're going to drop the unnamed 0 feature on axis 1. Then we're going to drop the, what was it called? Flight feature as well. And then we're going to do the simple binary encoding. So class is going to be equal to df class, and we're going to apply a lambda expression here. So we're going to apply a function. It takes some input x, and it will return basically 1 if it's business. So 1 if x equals business, else 0. So this will turn it into a binary feature. And then we can do also something similar to or for the stops. The thing about the stops is, let me just see if it makes more sense maybe to use factorize. So let's go with df stops. And then we're going to use, or actually we're going to do pd factorize. I don't use that function too often, which is why I have some notes about it here. So pd factorize df stops. I think this should work. I'm just not sure if this is going to result in what I want, because now, or actually it works, because 0 is 0, 1 is 1, or is it? I'm not sure. No, I think the problem with this is that the scale is not correct. Or the order is not correct, because now I think 0 is 0, 2 is 1, and then 1 is 2, which messes up the order, because since this is a numerical feature, the order is important because there's a progression between 0 and 2, and there's the 1 in between, so it means that the 1 is right in the middle, so 1 should actually be 1, 2 should actually be 2, and so on, which pd factorize does not do, at least not if we use it like this. Or actually, I'm not sure if that's even the case. Let me just see if maybe it's correct. So let's see df stops. We have 0, 0. Oh no, actually it works. I just messed it up because the order here was 0, 1, 2, and then I had 0 and then 1 at the end. But actually it's the correct mapping. So this already should be enough to do a proper factorization. So we can actually just go ahead and say df stops, or actually we can use df.stops is equal to pd factorize df stops. Or actually this doesn't work. Why doesn't it work? Because we need to go index 0 like this. And then we can also run this, and then we should already have some pre-processed stuff here. We have stops, and we have class as already encoded features. We dropped unnamed and flight. So the rest of them will be one hot encoded. And in order to do one hot encoding in pandas directly, we can just use the getDummies function. So we can say here df equals, and we're going to join together the data frame that we already have. So we're going to join the df that already exists, and we're going to join it with the dummies of the specific features. Now, maybe so that you can understand this better, what we're going to do is we're going to do pd getDummies onto a column. So let's say, for example, the airline. And what this will result in is we're going to have the airlines as individual columns that are all 0 except for 1. And this is going to be the actual airline. So we're taking a categorical feature and splitting it up into, in this case, 6 different features that are all 0 except for 1, which is the value that was the value in this particular row. So what we can also do is we can add a prefix just so we have a better overview. So prefix is going to be equal to airline. And then we're going to have these column names. And now we're going to join them with our data frame. So df join the data frame with the dummies. And this is going to result in this. And of course, what we also want to do is we want to drop the airline then. So we want to do drop airline axis 1. So this is what it would look like. And of course, now we want to do the replacement. So df is actually this whole thing. And we're going to do the same thing now for the different features. So we're going to do the same thing with the source city. Come on, where's the autocomplete? Okay, doesn't give me an autocomplete. Source city. We can say source is going to be the prefix source city, and then I'm going to do the same thing with the destination city. Let's just go with dest here. Destination city. And then we can go with what was it? Arrival time. Arrival time, and then departure time, departure time, departure, and departure time. And do we have anything else? I think that's it. So we can just run this and our data frame will finally look like this. We only have numerical and binary features left. We don't have any features that are not either numerical or binary, so we can feed all of this directly into a regression model. And the price, of course, has to be treated as the y value, as the target variable, but you can see the pre-processing is now basically done. So what we're going to do now is we're going to train a random forest regressor. So we're going to add a new section here. I'm going to call it training regression model. And we're going to say that we want to have from sklearn.ensemble, we want to import a random forest regressor. So a random forest regressor will be the model architecture or the model type that we use here. And of course, we need to also use from sklearn.model selection, we want to do a train test split. So we want to use a train test split to split the data into training data and testing data so that we can train a model and evaluate it with unseen data, with unfamiliar data. So x and y is going to be equal to the data frame when we drop the price column. So everything except the price is going to be part of x, and y is then also, y is then going to be the price column. So yeah, you can see the x values are these and the y value is this. So this is just the y data, the target variable. And now we're going to do x train, x test, y train, y test. And we're going to do train test split xy with a test size of 0.2. So 20% of the data is going to be used as testing data, 80% is going to be used for training. Now, what we can do here is we can ask, for example, now I'm showing you a feature of pieces here again. Let's say I want to train now a regression model. Let's say I say rec equals random forest regressor. And I want to do rec fit onto X train and Y train. Maybe I have some questions that I want to ask here. So this here is the code I want to ask a question about. I can just right click it and I can ask pieces about my selection. So I can right click it and I can say, how can I speed up this process, question mark. Now, of course, I know the answer in this case, but I'm just showing you an example. But basically, I'm waiting for a specific section. I think it mentioned it here somewhere. Utilize parallel processing. I can set n jobs to a value greater than 1. Now I can follow up and ask, how can I get the max number of processors? While I'm coding here, I can ask, and then I should... Okay, actually, it shows me a different solution here. You need to keep in mind, though, that this is, of course, GPT, so it's not really pieces that's giving the answers here. But the correct answer here would be, and I would probably get it if I ask more often, is I would get n jobs equals -1 to maximize the number of processors used. Now, what I can also do is I can ask, for example, do I need to scale my data for this type of model? And the correct answer would be no, because there you go. Yeah, you don't need to scale your data for a random forest regressor. So you can ask questions like these. You can also, by the way, set some context. Now you can add files and code snippets and folders and messages that are going to be considered when this assistant is giving answers to you. So you can just upload files and get some responses here as well. All right, so we can just fit the model here. And then once the training is done, we can also evaluate it immediately. We can say rec score on the test data and on the X test data and on the Y test data. And in this case, I get 98.55%. I mean, it's not accuracy. I think it's R squared. So it's it works like accuracy because it's between 0 and 1, and 1 is the perfect value. But it's basically just the R squared or the R2. I'm not sure what the correct name is in English. But that's the metric that we use here, and we can see that the performance is pretty good. Now, what we want to do, though, is we want to get some more metrics. We want to get some... first of all, we want to get some more metrics, and then we also want to increase the performance of this model by doing hyperparameter tuning. So what we're going to do is we're going to say from sklearn.metrics, we're going to import the mean absolute error, the mean squared error, and the R2 score, just to show you that this is actually the R2 score, or R squared score, whatever. And then we're also going to import math, because we want to do some square root stuff here as well. The reason you might be interested in a mean absolute error is because you want to know on average how much you deviate from the actual price in actual dollars, if this is dollars, I'm not sure, but in actual currency and not some abstract metric. So what we can do here is we can say y predicted values given the test data is going to be equal to the regression model predicting or making predictions on the test data. And then we want to compare these predictions to the actual values and calculate different scores. So the R2 score, I'm just going to call it R2 now. I think this is not wrong. It's going to be the R2 score and then Y test and Y predictions. And you can see this is the same value here. But now we can do the same thing with the mean absolute error, with the mean squared error, and also with the root mean squared error, so RMSE. So here we just have to do mean absolute error, mean squared error, and here we need to also do mean squared error, but we're going to go with a square root. So math.sqrt before that. There you go. So this is the thing that we can interpret. On average, our model makes a mistake or an error of 1066. So it's actually not that small of of a mistake here, but we can also visually see how close our predictions are to evaluate overall if our model performs well or not. So we can go ahead and say import matplotlib.pyplot as plt, and then I can say plt scatter, and I can scatter the predictions against the actual values. So I can say ytest, or the actual values against the predictions, ytest yprediction, and then plt x label is going to be actual values, or actual flight price, and then the y label is going to be predicted flight price, and then I can say plt title, and then prediction versus actual price. And then if I run this, you can see that our predictions sometimes are quite off, but overall, if you look at these axes here, we have a pretty tight, not line really, but the points are scattered around a line and they're not too far apart. So the variance is not huge, which means that the model is performing decently. We don't make some ridiculous predictions. And I also think, by the way, that when I look at these values now, that the price is probably not in dollars, which means that if we go and say actually df price, and then actually, can we do something like describe? Was it describe? Yeah, there you go. If you look at it, the mean price is 20,000, the minimum price is this, and the maximum price is this. So actually a deviation in our predictions of 1,000, if it was dollars, it would probably be very horrible, but I think this is some Indian currency here, since these are Indian cities. And in this case, probably this is actually quite a small error that we're making here. So our model is pretty strong. And you can see that here because, as I said, the points are quite close to one another, or quite close to the line here that is running through the middle. All right, so let's go ahead and see also, before we go to the hyperparameter tuning, which kinds of features are the most relevant for this. So what we can do for this, again, just to show you pieces, is we can go and say sorted feature importances random forest regressor, and then I can get my extension here. I can copy and save the snippet. I can go to my Jupyter Lab environment, and I can just copy paste this here. Now, of course, we should look at the code to understand what it's doing, because what we do here is we have an empty dictionary, and then we iterate over the feature importances that are already built into our regression model. Now we need to replace RF, the random forest, with our rec model, which is our actual model. We iterate over these feature importances, and then we add them to the dictionary with index and value here. So index being just the enumerate index and value being the actual feature importance. And then we get our feature importances list, which is the sorted dictionary where the key is the element that we get with get. We sort it in reverse order, and then we can print the most important features. Actually, this is some pretty shitty code, to be honest. So I wanted to show you the feature, but the code doesn't impress me a lot. So I'm going to do it my way. I'm going to say importances is equal to dictionary, and we're going to zip the feature names with the feature importances. And then we're going to just get the sorted importances by saying sorted, not sorted importances, sorted, and then importances items key is going to be a lambda expression where we get x, x1, and reverse is going to be true. And then we can print these sorted importances. There you go. And of course, we can also go ahead and save the active cell to pieces. So I can go and I can save this to pieces. And now I have my own snippet that I can use later on. So if I ever have to do the same thing, I can just go here and I can copy paste this snippet to get my feature importances, because that from Stack Overflow, I did not like that. So I can just find my own solution and save it for future work by just clicking this button, saving it to snippets. There you go. Yeah, so as you can see, the most important feature by far is the class. So I think this was predictable. Business economy is gonna be a huge difference. Also, the duration is very important, and when you book the flight, 1 day before, or 10 months before, probably. I'm not sure what the range here is, but did we actually look at that? Did we look at the range of the days left? Let me just check that. Let's go df days left, describe. Yeah, so max is 49. Okay, so we don't have that much of a time horizon here. But yeah, you can see a very unimportant feature seems to be the airline. The airline doesn't make a huge difference, as it seems. Yeah, so you can look at these feature importances, interpret them, you can plot them, and so on. Actually, let's go ahead and plot them. Let's go ahead and say PLT figure, we're gonna say figure size is equal to 10.6 to keep it not too huge here. And we're gonna do a bar plot. We're gonna say x0 for x in sorted importances, but only the first 5, so the top 5. These are gonna be the x values, and then x1 for x in sorted importances up until 5 is gonna be the y values. Like this, there you go. So we have a nice visualization. We can also change this, of course, to 10 if we want to see more features. But probably then we should use a different figure size. There you go. So yeah, this is how you can visualize it. Now let's go to the final step, which is the hyperparameter tuning. For those of you who don't know what a hyperparameter tuning is, it's basically fine-tuning this is now redundant, fine-tuning the hyperparameters, meaning that when we train a random forest regressor, we have certain variables that we can adjust, certain parameters that we can adjust. So if I say random forest regressor sklearn, and I go to the documentation, you can see that I have the number of estimators, I have the criterion, I have the max depth, I have the min sample split, and so on. And these are all parameters that I can adjust to get maybe a better or worse result. And I also should be able to see, no, it doesn't show me some code samples here. But yeah, this is what we can adjust. We can try different configurations, but instead of doing this manually, instead of going up here now and constantly trying to go with a different set of hyperparameters by saying, okay, min sample split is equal to something, and then number of estimators is equal to something, and so on. I can do it in an automated way. I can use grid search or randomized search using cross-validation. So this is what we're going to do for this video here. So what I'm going to do is I'm going to say from sklearn.model selection import grid search CV. And the idea of grid search is that you provide different values that you want to try for the different hyperparameters. And of course, if you have different features and different values, you have different combinations. So if I have, let me just give you a basic example. If I have parameter 1 and I have the values A, B, C, and then I have parameter 2 and I have the values X, Y, Z, then of course I have not just 3 combinations to try, I have all these combinations to try. So I have to try AX, I have to try AY, AZ, then BX, BY, BZ, and so on. So basically I have to multiply all these combinations. And this is done automatically using a parameter grid. So what I can do is I can say param grid is going to be equal to a dictionary, and I'm mapping the feature names to collections or to lists of values that I want to try. So I'm going to go and say n estimators, which is one of the hyperparameters. N estimators is going to be equal, or it's going to be mapped to 100, 200, 300, for example. And then I can do something like the max depth of the tree is going to be equal to either none, so no limitation, or to 10, 20, 30. And then I can go with min samples split, and then I'm going to go and say 2, 5, 10. And then I can say min samples leaf. And then again, I can say 1, 2, 4. And finally, let's go with the max features. And you can decide which ones you want to use. Probably it's good to include the default value and some values around it if possible. And then you can test the edges. So if I do this grid search and I see that 300 is the best number for n estimators, I might suspect that 500 might even be better. So I can maybe try that again. But for the max features, we're going to go auto and SQRT. Now this would be a parameter grid for our grid search, and what I can do now is I can ask here to show you the feature again. I can ask, actually I need to mark all this. I can ask, how do I now do a grid search? So I can say, ask pieces about selection, how to do a grid search now. And then I should get a give me the code. There you go. So I can just copy this now. I can replace this. I have the same parameters and basically just did what I wanted to do anyways. It did a grid search CV using the estimator. In our case, this is going to be the regression model. Maybe we should create a new one. So let's go and say rec equals random forest regressor and jobs equals -1. And then we have a cross validation, which is 5-fold. Then we fit our grid search on it and we get the best parameters. Now, we're not going to run this because this is going to take forever. You can calculate how many combinations you have here. You basically just have to multiply all these. So you can say 3 times 4 times 3 times 3 times 2. So we have 216 combinations and one already takes quite some time. So we're not going to run this. If you have, however, a lot of time, or if you need to do this, or if you are training on data or using a model that doesn't take too much time, you can do that, of course, but now it would just take forever. So what we're going to do instead is we're going to do something else. We're going to do a randomized search cross-validation, which means that instead of going for all these values, we're going to provide ranges and we're going to try to get lucky and to just pick values that work. So we're going to do way less attempts. We're going to do just 6 fits in this case instead of 216, but we're going to just hope that we end up with some decent values. So we're going to say from sklearn model selection, import randomized search CV, and then also for this we're going to need to install a Python package, pip3 install scipy, just so we can generate random values. We're going to say from scipy stats, we're going to import scipy stats, we're going to import randint. And then we're going to say that now we're not going to have a parameter grid, but a parameter distribution. And here we're going to do the same thing. We're going to use the same feature, so I can copy this. But instead of actually providing concrete values, we're going to provide ranges and possible values, but we're going to then allow the randomized search to just pick some of them. So here, instead of providing these 3 values, we're going to say randint from 100 to 300. So anything in between goes as well. Then for the max depth, we're going to provide these values. We're going to also provide some more values, 40, 50. It doesn't really matter because providing more values is not going to mean that you do more work because the picking is still random. So you're still not going to do more of the iterations just because you add some more possible values here. Here we're going to do another randint from 2 to 11. And here we're going to go with a randint from 1 to 5. And here we're going to have still these 2 options. And also, I think that, was it the default was 1.0? Not sure about that. That is the distribution. And now to actually run this, to actually run a randomized search with cross-validation, again, we say rec equals random forest regressor and jobs is -1. And we say random search is equal to randomized search CV. And the estimator is our regression tree or regression forest. The parameter distribution is equal to param_dist, our dictionary. We're going to do 2 iterations, and we're going to do 3-fold cross-validation. Now, 3-fold cross-validation means we split the data into 3 folds. We train on 2, evaluate on 1, and we iterate this so that we basically try all these combinations. Maybe to just briefly explain this, I have a video on this already. Let's say this is all of my data. Now I can split it into 5 folds, like this, 1, 2, 3, 4, 5. And what I do is I train my model on all these and I evaluate it on this one. Then what I do is I train on all these and I evaluate on this one. Then what I do is I train on this and these and I evaluate on this one, and so on. So I do this for all the combinations. This is the idea of 5-fold cross-validation. In this case, we're going to do 3, so we only have 3 times 2 fits. Then we're going to do scoring is going to be equal to negative mean squared error. And we're going to say verbose equals 2 because we want to see the progress. And we're going to provide a random state of 10 so that this is consistent. And I'm going to say njobs equals -1 here as well. And then we're going to do the actual search, random search dot fit xtrain, ytrain, and then we're going to get the best estimator. So best regressor is going to be equal to random search best estimator. So I can run this now. And of course I have a problem. What's the problem? Perhaps you forgot a comma. Why is that? Oh, yeah, because I forgot a comma. There you go. So totaling 6 fits. We're going to wait for this to finish and then we can look at the results. Okay, so we're done with the randomized search now. We can go ahead and see if our best regressor actually outperforms the one that we previously had. So score X test and Y test. Now this is not always going to be the case, especially when you do a randomized search CV. But let's see, we have 98.64 R2 score, and above we had, I think, 98.55. So this is already better. Now we can copy paste this and see if we get better results in all the metrics. What's the problem here? Oh, I don't want to use rec. I want to use best regressor. And I get 1080. What did I get before? 1066. So here it actually was lower. And then for the other values, this one is, how much is this? This is 6 million, 6.9 million. And up here we had 7.4 million. So this one is better. And then we have here 2,728 and 2,641. So it seems to perform a bit better. I can also go and copy paste this here to actually plot the results. Yeah, doesn't look too bad. So in this case, it seems to have improved the performance. It's not always going to be the case, especially not if you just use 6 fits. But if you use a grid search or if you do a more comprehensive randomized search, probably you're going to get an improvement most of the time from hyperparameter tuning. All right, so we successfully went through the machine learning process. We completed the project. We trained a regressor to predict flight prices, and it performs quite well. So if you have some data that's similar to this one with the same locations, the same airlines, and so on, you can just go ahead and use the best regressor to do a predict on the data that you provide, the same way that you did it here, or we did it here for the X test data. Just provide it as a pandas data frame, and then we can do predictions. And predict the flight prices. And of course, if you have a different data set, the process is probably going to be quite similar. So yeah, this is the full machine learning process. Now let me get back one more time to pieces. So for those of you interested in pieces, again, it's a very powerful integrated environment, an integrated copilot. It helps you across multiple different tools. As I said, you can use it in JupyterLab, you can use it in PyCharm VS Code, you can use it on a desktop. Again, I can just open up pieces for developers. I can browse my snippets, I can ask questions. I can go and say here, for example, flat list, and I will get my flattening nested list. I can modify it. I can see where exactly I got this from. This is also interesting. I can not just save the snippet, I also know where I saved it from, so I can go back and visit the website if I'm interested in that. all in all, it's just a very nice integration, and also with the Copilot and the feature that you can also use local LLMs for more privacy, everything stored on your system, is a very nice and powerful tool. So if you're interested in it, check it out in the description down below. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.